Hello and welcome to our short presentation about homoscedasticity. What sounds pretty hard is actually quite simple, and we'll guide you through it step by step. First, we're going to talk about the underlying concept, variance. Secondly, we're going to define homoscedasticity for you, and afterwards we're going to put it in the context of the lecture and therefore show you why you need it. In the end, we're going to show you when to assume homoscedasticity and what negative effect it brings if you assume it wrongly. But first, let's talk about variance. Later you'll see why. Variance shows you how far your data points are spread from the mean, so the average of all data. It is computed by taking the standard deviation squared. We won't go deeper into the standard deviation, but if you're interested in the formula, you can pause the video here. Enough about variance, let's talk about homoscedasticity. Honestly, one of the hardest parts for me is the pronunciation. So I'll show you a little trick. You have to divide it into three parts. Homoscedasticity. Again after me. Homoscedasticity. You might ask yourself, what do we need variance for now? The answer is hidden in the name, as homo means same and scedasticity actually means variance. And this is basically all this concept is about. Same variance for all our data points. As you can see in the picture, this obviously doesn't mean all data points having the same distance to our regression line. It simply means all, or at least most, values are spread somewhere within the same range, namely variance, a homogenic deviation of data points. So what we have here is our independent or predictive variables plotted on the x-axis, and our dependent or outcome variable plotted on the y-axis. The red regression line models the relation between both these variables. It can only do this since our data points are spread homoscedastic. But more about this on the next slide.
I want to show you in what context you will find homoscedasticity in the lecture. And for that, let's have a look at this plot. You see some data points, for example from some experiment you made. And let's say you want to find a fitting model that is able to predict such data. I guess you wouldn't come up with such a model, because if you would repeat the experiment, you wouldn't expect exactly the same outcome, but rather that there are some errors in the data from the first experiment. Instead, you would come up with a flexible function, here a sinus curve, and accept the difference between the observed value and the predicted value, marked in orange as errors or noise. And that is called linear regression, because you model the linear relationship between the target variable and the independent variable. And that is a process that you can repeat several times to find a model that is most likely to predict the data correctly. This means the regression model is composed of an underlying function and a function for the noise. Now you need to know how to model the noise. As you can see in this plot, the noise should be normally distributed, so that most of the data points are close to the mean mu. Also, our aim is to minimize the variance, so we try to make the likelihood function more steep. Here I'm going to show you why. If we layer the noise distribution in blue on top of our linear regression model with a mean equal to 0, so that we get the middle of the normal distribution right on top of the predicted data point, then we can see where a data point will lay with which likelihood. So, assuming that our regression model is fitting, the observed data point is most likely to be very close to the regression line. Now, what has that to do with homoscedasticity? Well, as Fabio already explained, homoscedasticity means that the variance of each point remains constant along the regression line. So for the regression model to meet the assumption of homoscedasticity, the same error distribution should be applicable at every point of the regression line. To put this in a formula, T of x is the overall model that predicts the target data. Our underlying function is the sinus curve, here marked in red, and then we add the noise marked in blue, which is a likelihood function of t given that the mean mu is 0 and sigma, the square root of the variance, stays constant.
We assume homoscedasticity when trying to do a regression analysis. If a linear model is used, homoscedasticity is essential as it's the underlying assumption. The spread of residuals must be constant in linear regression, therefore we assume homoscedasticity when assuming a linear regression. Also, the predicted results might become untrustworthy if this assumption is violated, as a regression model cannot be used. So what are the ramifications of a false assumption? First of all, regression analysis could be unfitting if the data is heteroscedastic, as the assumption underlying this analysis is violated. The further predictions could have a larger error margin, which would render the model useless. Assuming a variable is homoscedastic when in reality it is heteroscedastic results in unbiased but inefficient point estimates and in biased estimates of standard errors, and may result in overestimating the goodness of a fit as measured by the Pearson coefficient.